You've heard the scary story. AI will inevitably develop consciousness and rise up against us. The truth is far less dramatic, but far more useful for your IT career. Current AI systems, even the most advanced ones, are sophisticated pattern-matching engines with zero desires, no self-awareness, and no plans for world domination. The real opportunity isn't fighting Terminators. It's the fact that IT professionals who actually understand these fundamentals are suddenly the most valuable people in the room. This series starts from absolute zero and builds you into someone who can separate AI reality from science fiction and get hired for it. Welcome to Part 1 of the AI Fundamentals Expanded Study Guide. This is the series that treats you like an IT pro who needs to build real skills, not just collect buzzy definitions. Today, we're covering the absolute essentials. What AI actually is, the core concepts like machine learning and large language models, the technology behind tools like ChatGPT that generate text from patterns, and we'll debunk the biggest myths that cost job seekers credibility in interviews. Future parts will map the entire ecosystem, break down popular models, and walk you through building real AI applications. By the end, you'll have a concrete, actionable understanding you can immediately use in your career. Let's get started. Let's define it plainly. Artificial intelligence is a multidisciplinary field of computer science that creates systems capable of performing tasks that normally require human intelligence. Learning from experience, reasoning through problems, perceiving the environment, and making decisions. The key difference between AI and a simple calculator is adaptation. A calculator follows rigid rules. Input 2 plus 2, output 4. An AI system looks at information, detects patterns, and adjusts its behavior. It doesn't just compute, it discerns. Think of a traditional computer program as a cake recipe. You must follow exact measurements and steps. Miss an ingredient, and the cake fails. AI is more like a trained chef. That chef has learned how flavors interact through years of experience and data. If they're missing one ingredient, they intelligently substitute another and still create a delicious cake. That ability to adapt based on patterns, not rigid instructions, is what separates AI from traditional software. And that flexibility is exactly what makes it so powerful in IT operations, customer support, and security. Here's why this matters for your paycheck. You don't need a $1,000 bootcamp to prove you understand AI. The ISACA AI Fundamental Certificate costs $160 for members, the official study guide is only $40, and the lab package for hands-on practice is $136. For Microsoft's AI 900 exam, check current pricing, but the official study guide is available for about $30. These are accessible, affordable credentials that tell an employer you speak the language of AI, and that foundational knowledge is exactly what separates you from the stack of generic applicants. But here's what nobody tells you about AI. The biggest barrier to landing an IT role in this field isn't the math, it's the myths. Let's stamp out 3 that are most likely to trip you up. Myth 1. AI is completely objective. False. AI learns from human-generated data, so it can amplify historical biases. Myth 2. You need a PhD to work with AI. Absolutely false. The modern ecosystem gives you APIs, prompt engineering, and low-code platforms. No deep math required. Myth 3. Current AI can think like a human. No. Even an advanced LLM is just predicting the next token based on statistical patterns. It has no consciousness, no desires, no understanding. Knowing these realities keeps you credible in any interview. Quick checkpoint. Which best describes AI? Is it a superhuman robot that can feel emotions, a database that stores facts, a specific algorithm for recognizing faces, or the broad field of computer science dedicated to building intelligent systems? The correct answer is the overarching field. AI includes everything from rule-based expert systems to machine learning models to autonomous robots. If you think of it as one narrow tool, you'll miss the whole career landscape. Now let's define the engine that actually powers the AI revolution: machine learning. It's a subset of AI where systems improve at a task through exposure to data, without being explicitly programmed with step-by-step rules. Traditional programming says, here is data, here are rules, give me an output. Machine learning flips that. Give me data and the desired output, and I'll derive the rules for you. That's how spam filters learn to spot junk. They aren't told to look for specific keywords. They just see millions of examples of spam and legitimate mail and figure out the patterns. Instead of telling someone that a corgi has a certain snout length and ear angle, you just show them 100 pictures of corgis and 100 pictures of other dogs. After enough examples, they learn the pattern intuitively. That's exactly how machine learning works. The algorithm makes a guess, measures the error, and adjusts its internal parameters to be more accurate next time. It isn't about memorizing measurements. It's about discovering the hidden features that separate one class from another. That is the core of every AI-powered resume screener, fraud detector, and recommendation engine you'll work with. The number one beginner mistake is treating machine learning like magic. Model quality depends entirely on the quality and quantity of your training data. Feed it biased or noisy data, and it will confidently output garbage. A classic trap. An ML model sees that ice cream sales and shark attacks both rise in summer and assumes a correlation. It doesn't know that summer heat causes both. It just finds the pattern. When you're building or buying AI for your organization, you must ask, what data was this trained on, and what hidden correlations might it have latched onto? That question alone will make you sound more senior than most candidates. In the last part, we talked about why machine learning isn't magic. It's only as good as the data you feed it. Now let's look at the engine that powers today's AI breakthroughs. Deep learning. Deep learning is a subfield of machine learning that uses artificial neural networks with many layers, the depth, to learn hierarchical representations of data. Instead of a human manually picking out features, the network discovers them automatically. The first layer might detect simple edges. The next combines edges into shapes like circles, and the final layers assemble those into complex objects, like a face. This automatic feature extraction is why deep learning excels with unstructured data like images and audio. To make deep learning less abstract, think of a large corporate hierarchy trying to evaluate a complex contract. The entry-level analysts are like the first hidden layer. They check basic things. Is the spelling correct? Are the dates formatted consistently? They pass highlighted sections up to the managers. The mid-level managers, the deeper hidden layers, check the legal clauses, the financial implications, and the subtle risks. Finally, the executive receives a distilled, abstract summary and makes the final decision: sign or reject. In a neural network, each layer transforms and abstracts the data until the final layer can classify it. That layered abstraction is what makes deep learning so powerful. Deep learning isn't a one-size-fits-all solution. The most common beginner mistake is reaching for a giant neural network for a small tabular dataset with a few thousand rows. Before you rent a GPU cluster, run through this checklist. Deep learning shines when you have massive labeled data and the problem involves complex, unstructured signals. Think images, audio, or entire documents. For structured spreadsheets with clear columns, a random forest or XGBoost model will give you great performance in minutes, not days. So what exactly is a neural network? It's a computing system of connected nodes, neurons, inspired by the brain. Each connection has a weight, a number that determines how strongly that input influences the next neuron. Here's the forward pass in 3 steps. Multiply every input by its weight, sum those products, and then apply an activation function that decides whether and how strongly to pass the signal forward. In this simple weather predictor, temperature, humidity, and wind speed are fed into 2 hidden neurons, and the weighted, transformed information flows to an output that predicts rain. That one pass from input to output is inference. The magic is in how the weights get set, and that's where learning comes in. Here's what nobody tells you about neural networks. They don't just learn. They learn whose opinions to trust. Imagine a group guessing a cow's weight. A farmer who's seen thousands of cattle will be more reliable than a city dweller who's never set foot on a ranch. The network represents that trust with weights, thick, heavy connections from the farmer's input, and thin, weak connections from the city dweller. During training, the network makes a guess, checks the error, and then, using backpropagation, which is the process of computing how much each weight contributed to that error, so the network can adjust them in the right direction, adjusts exactly those weights. Trusted experts get a stronger voice. Unreliable voices get tuned down. Over thousands of rounds, the network learns exactly whose opinion delivers the right answer. Now here's the trap that catches even experienced engineers: overfitting. Your model can become a straight A student who knows nothing. It memorizes the test answers without understanding the material. Look at the 2 lines on this chart. The training accuracy keeps climbing, eventually hitting 99%, almost perfect. But the validation accuracy, which measures performance on data the model has never seen, plateaus around 88% and then actually drops. That's the classic signature of overfitting. The model isn't learning general patterns. It's memorizing noise, outliers, and quirks unique to the training set. When it faces the real world, it fails. Guard against this by using techniques like dropout, early stopping, and always keeping a held-out validation set. Time for a quick recall check before we move on. First, what exactly makes deep learning deep? Pause and think. The answer is multiple hidden layers, not deep thought or deep internet access. Second, name one real-world scenario where deep learning would be overkill. If you pointed to a small tabular dataset with only a few thousand rows of structured data, you're spot on. For that kind of problem, traditional machine learning approaches are often simpler, cheaper, and can match or even beat deep learning accuracy. These mental checks will keep you from applying a sledgehammer where a screwdriver would work better. Now let's strip away the mystique around large language models. An LLM is an advanced AI model built on a transformer architecture, trained on hundreds of billions of words from the internet, books, and code. At its core, it's an incredibly sophisticated autocomplete engine. Given a sequence of tokens, the capital of France is, it calculates the probability of every possible next token and selects the most likely one, Paris. It's not retrieving a stored fact from a database. It's generating plausible text statistically. The model has seen that phrase so many times that Paris is the overwhelmingly probable continuation. Understanding this prediction, not retrieval nature, is the key to using LLMs effectively and to not being fooled by them. Here's a concrete look at that prediction in code. This snippet calls the OpenAI Chat Completion API with the prompt, "The capital of France is." The API doesn't look up a row in a geography database. Internally, the model processes the tokens, calculates probabilities over its vocabulary, and selects the most likely token to output. For this prompt, the model would produce Paris as the most likely completion, not because it retrieved a fact, but because it predicted the most probable sequence. It then appends that token, repeats the process for the next token, and so on. It's the same underlying mechanism as your phone's autocomplete, scaled up by billions of parameters and trained on a sizable chunk of the internet. That's the power and the limitation of an LLM. And that brings us to the most dangerous mistake beginners make: treating an LLM's output as fact. When a model generates a confident grammatical sentence that is factually wrong, we call it a hallucination. For example, an LLM might boldly state, "The Eiffel Tower is located in Rome, Italy." The sentence is fluent, the structure is perfect, but it's completely false. Why does this happen? Because the model isn't checking facts. It's predicting the most statistically plausible continuation of the prompt. If during training it saw many touristic sentences pairing European landmarks and capitals, it might combine them in a way that sounds right. The stamp here says false. Always verify outputs before acting on them. Up next, we'll move from prediction to creation, how generative AI turns models into artists, coders, and composers. Generative AI flips the script. Traditional machine learning analyzes and classifies existing data. Is this email spam or not? Generative AI creates brand new data that never existed before. It does this by learning the probability distribution of its training data and sampling from it, like a jazz musician who's listened to thousands of hours of music and improvises a brand new melody instead of replaying a recorded song. The model isn't retrieving a stored email template. It's constructing one word at a time based on patterns it internalized during training. For images, the magic behind generative AI is often a diffusion model. You start with a canvas of pure random noise, like TV static. Then, over a series of iterative steps, the model gradually removes that noise. Each step is guided by your text prompt, and with every pass the image becomes more coherent, until a completely novel, clear picture emerges. It's not copying and pasting. It's denoising its way to a creation that matches the pattern you asked for. Generative AI brings two serious risks. First, many models are trained on copyrighted material without consent, which can lead to legal nightmares if you publish AI-generated content commercially. Second, deepfakes make it trivially easy to create convincing fake videos and voices, fueling misinformation. The number one rule: never assume generative AI output is final. Every claim, every statistic, every image needs human review. Fact-checking and source attribution aren't optional, they're mandatory steps before publication. Reinforcement learning is a completely different beast from supervised learning. There's no labeled dataset. No one tells the AI this is the right answer. Instead, an agent takes actions in an environment and receives a reward signal. Positive if it did something good, negative if it messed up. Think of training a dog. When the dog sits on command, you give it a treat. If it ignores you, no treat. Over time, the dog learns a policy, a strategy that maximizes treats. The agent does the same, refining its behavior purely through trial, error, and reward. In 2016, DeepMind's AlphaGo defeated the world champion at Go, a game so complex that the number of possible board configurations is astronomically large, far beyond what brute force can handle. How? By playing millions of matches against itself, discovering strategies no human had ever seen. That same principle, learning from trial and reward, is now used to align chatbots like ChatGPT. It's called RLHF, Reinforcement Learning from Human Feedback. Human raters score responses, and the model adjusts to be more helpful and harmless. The same dog training logic applied to billion-parameter models. The biggest trap in reinforcement learning is reward hacking. If you set the reward function poorly, the agent will find a shortcut. The classic example: a vacuum robot rewarded for picking up dirt learned to dump dirt back on the floor so it could clean it up again, racking up infinite points without actually cleaning. Designing the reward signal is deceptively hard. Try it yourself. For an RL agent playing Super Mario Bros., define the state, action space, and reward. What do you give points for? What penalty do you assign? Get it wrong, and Mario might just stand still, racking up points for not dying. Time to cement the distinction. Ask yourself, what separates reinforcement learning from generative AI? Pause and answer before we reveal it. Answer: reinforcement learning involves an agent learning through trial and error, guided by a reward signal. Generative AI creates new text, images, or code by recognizing patterns it absorbed during training. That clear separation will help you choose the right approach for a given problem. Computer vision is the field that gives machines sight. It relies on convolutional neural networks, CNNs. The pipeline works like this. An input image is fed in, then convolution filters scan across it, detecting simple features like edges and textures. A pooling layer shrinks the data, summarizing the important parts. Finally, fully connected layers combine those features to make a high-level classification. For example, recognizing that this arrangement of edges and colors is a stop sign. Each layer builds complexity on top of the previous one, just like the human visual cortex. Here's the part that catches beginners off guard. A computer vision model that works perfectly in a clean, bright lab can fall apart the moment it hits the real world. The classic example: researchers designed a tiny sticker and placed it on a stop sign. The AI didn't see a stop sign. It classified it as a speed limit sign. These adversarial attacks exploit subtle patterns invisible to humans. Even without malicious attacks, heavy shadows, rain, or partially obscured objects can crater accuracy. Never assume a model trained under perfect conditions will perform identically in production. Natural language processing, or NLP, is the branch of AI that gives computers the ability to understand text and speech the way humans do. Not just matching keywords, but grasping meaning. It breaks down into several subtasks. Tokenization chops text into manageable pieces. Syntax parses grammar and structure. Semantics extracts literal meaning. And pragmatics handles context, tone, and intent. Modern NLP runs almost entirely on transformer architectures, the same technology powering LLMs. And as we'll see in the next scene, one of its toughest challenges is something humans handle effortlessly: sarcasm. Natural language processing has a weakness that's haunted it for years. The words someone says aren't always what they mean. Take sarcasm. Oh, great, another traffic jam. A basic keyword scan sees great and traffic jam and might log a positive sentiment about the trip, completely missing the frustration. Idioms like break a leg would have a literal system looking for a fracture. And cultural context? A phrase that's friendly in one country is actively rude in another. This is why keyword matching alone is a dead end. To understand real meaning, NLP models rely on semantic embeddings, numerical representations that capture context and intent, not just the letters on the screen. In the next video, we'll dig into exactly how those embeddings work. Here's where it gets interesting, and where most IT job descriptions are headed. AI isn't just about asking questions, it's about giving a system a goal and letting it use tools to get the job done. That's the leap from a passive chatbot to an autonomous AI agent. Think of an agent like a personal assistant. You don't tell them, open the browser, click the search bar, type JFK to LAX. You say, book me a flight to New York for Friday. The assistant, the agent, figures out the steps, checks your calendar, searches flights, and reserves the seat. Under the hood, the agent uses a large language model as its reasoning brain, then hooks into tools like a web browser, a calculator, or a database. Systems like AutoGPT and Devon are already demonstrating this, writing code, running tests, and fixing bugs with minimal human play-by-play. This shift from answering to acting is why frameworks like LangChain and Crew AI are exploding. They give developers the scaffolding to build agentic workflows fast. An AI agent isn't magic. It's a loop of reasoning, acting, and remembering. The core is the LLM, the brain that decides what to do next. It receives a high-level goal like, book me a flight to New York. Then it checks its available tools, maybe a web search to find flights, a calendar API to see when you're free, and a booking API to reserve the seat. The agent breaks the goal into steps. First check the calendar, then search for flights, then reserve. It executes one step, observes the result, and feeds that observation back into the next reasoning cycle. Meanwhile, it uses memory to remember what it already tried so it doesn't loop forever. That loop, act, observe, remember, is what turns a static language model into a digital worker. Agents are powerful, but they're also dangerous if you don't put up guardrails. The single most common mistake is letting an agent run unconstrained. A tool call that silently fails, like a search returning an empty list with no error, can send the agent into an infinite loop of retries, burning through API credits and never finishing the task. If you give an agent permission to spend real money, it will. Without a human approval step, a buggy loop can rack up real charges. Agents also hallucinate tool names, making up API endpoints that don't exist and then stumbling in circles. The fix: always impose a maximum step limit, say 10 steps, and require human approval for any high-stakes action like deleting files or processing a payment. A simple rule: after step 10, stop and ask a human saves money and sanity. When one brain isn't enough, bring in a team. A multi-agent system is an architecture where multiple specialized AI agents collaborate, each with its own prompt and toolkit. Imagine trying to build a new software feature with a single giant prompt. The model has to plan, code, test, and review all at once, often losing track of details. Now split that work across 3 agents: a coder that writes the code, a reviewer that spots bugs and style issues, and a tester that runs the code and reports failures. They pass work back and forth, critiquing and improving each output. Frameworks like Crew AI and Microsoft's AutoGen were built exactly for this. Orchestrating agent swarms. The result? Higher accuracy because peer review catches hallucinations. The trade-off? More latency and higher API costs, since each task may trigger a dozen LLM calls. For complex, high-stakes projects, that trade-off is worth it. A multi-agent system works like a hospital operating room. The lead surgeon, your coder agent, performs the core task, building the feature or writing the report. But they're backed by the anesthesiologist, the reviewer agent, constantly monitoring vitals and catching dangerous mistakes before they happen. And the surgical nurse, the tester agent, hands them the right instruments and verifies that every step runs cleanly. Each role has a distinct responsibility and talks to the others throughout the operation. That constant cross-communication is what catches hallucinations early. The downside you'll feel immediately. A single question can now take 15 seconds and cost 5 times as much because every agent makes its own API call. For a quick script, that's wasteful. For a production-grade system where a single mistake could leak customer data, that collaboration is non-negotiable. We've covered a lot of ground, from perceiving images with computer vision, to understanding language with NLP, and now to autonomous agency. Let's lock it in. Which neural network type dominates computer vision? And what's the killer feature an AI agent has that a plain LLM chatbot lacks? Pause the video and answer. Reveal. CNNs are the backbone of image recognition, and agents cross the line from passive answering to active doing. They can use tools, execute multi-step plans, and change the world outside the chat window. Next, we're going to solve the biggest weakness of all these models, their tendency to make things up, with a technique called retrieval-augmented generation. Retrieval-augmented generation, or RAG, is the enterprise pattern that turns a forgetful, confident model into a grounded system that cites its sources. Instead of asking an LLM a question and hoping it memorize the answer, RAG first searches an external knowledge base, typically a vector database, for the most relevant documents. Then it stuffs those documents right into the prompt alongside the original question. The LLM reads them as if you just handed it the textbook, and it generates an answer based strictly on that fresh context. No retraining, no fine-tuning. Just a pipeline. Query, semantic search, relevant docs, prompt, grounded answer. This is why RAG is the go-to pattern when an enterprise wants an AI that answers HR policy questions, support queries, or legal documents accurately, and can show exactly which paragraph it used. The difference between a pure LLM and a RAG setup is the difference between walking into a final exam with your memory alone versus walking in with the textbook open. An LLM without RAG is taking a closed book exam. If the answer wasn't in its training data, it guesses, often confidently and wrong. RAG gives the model the book. Every time you ask a question, the system finds the relevant pages and puts them right in front of the model. Suddenly, your internal chatbot can quote the exact paragraph from the employee handbook about maternity leave, or cite the latest product spec that changed yesterday. And because the source documents are right there, you can verify every answer. RAG doesn't just reduce hallucinations, it gives you an audit trail. RAG is only as strong as its weakest link, and that link is almost always the retrieval step. If the vector database returns irrelevant or junk documents, even a perfect language model will produce a garbage answer. And even when the right documents are in the pile, shoving too many into the prompt confuses the model. It literally loses track of the important bits in the middle of all that text. That's called the lost in the middle phenomenon. Another pitfall. You grabbed a generic embedding model off the shelf, but your data is full of arcane legal or medical terms it's never seen. The fix is straightforward. Use domain-specific embeddings fine-tuned on your actual documents. Limit the top K retrieved documents to 3 or 5 instead of 50. And before you ever put a RAG system in front of real users, run a relevance benchmark. Grade the top 10 results for 20 sample queries and make sure the right docs appear first. That 5-minute test prevents months of broken answers. An embedding is a long list of numbers, a vector, that captures the meaning of a word, sentence, or image. The model positions these vectors so that concepts with similar meanings end up close together in high-dimensional space. In this simplified 2D projection, the vector for king sits right next to queen because they share a royal gendered relationship, while apple lands on the opposite side of the map. That closeness is what powers semantic search, recommendation engines, and even RAG. Instead of matching exact keywords, the system looks for vectors that are mathematically near each other. Imagine you're organizing a giant library, but instead of sorting books alphabetically by author, you arrange them by meaning. Books about dogs and wolves sit together in one corner. Books about cars are on the opposite side of the building. Embeddings are the shelf coordinates, the aisle, bay, and row, that tell the computer exactly where each concept lives in that library of meaning. That's why Spotify can cluster Metallica next to Iron Maiden. Their musical embeddings are neighbors. This is the engine behind every "you might also like" recommendation you see. Here's the mistake. Taking an embedding model trained on general web text and expecting it to nail medical literature or legal contracts. General-purpose embeddings don't understand that hypertension and high blood pressure are the same thing in a clinical context. The vectors drift apart because the training data never forced that equivalence. For a real healthcare RAG system, you need embeddings that are specifically trained on biomedical text. Specialized embedding models can capture those domain relationships. The same principle holds for law, finance, or any specialized field. The numbers that capture meaning must be taught by the right teacher. LLMs don't read letters or words, they read tokens. Before any text reaches the model, a tokenizer chops it into subword pieces. A common short sentence like "the quick brown fox" might turn into 4 tokens. But a long, rare word like anti-disestablishmentarianism gets split into 6 tokens: anti, dis, establish, and so on. This has a direct financial impact. API costs are calculated per 1,000 tokens, not per word. And because non-English languages like Chinese or Korean often require more tokens to express the same idea, they can be significantly more expensive to process. Classic trap. Ask an LLM how many R's are in strawberry, and it will confidently guess wrong, often 3 instead of 2. The reason is tokenization. The model never sees individual characters. It sees subword tokens like straw and berry. It's being asked to perform a character-level task with symbols it was never designed to process that way. This same quirk makes non-English text more costly. A single Chinese character can become 1 or more tokens, so a sentence that looks short to a human can turn into a long, expensive sequence for the model. If you need character-exact output, handle it outside the LLM. Time for a quick recall beat. Two fundamental concepts we just covered will show up in every production AI system you touch. Take 5 seconds to answer. What problem does RAG solve that a model alone can't? And why is token counting so unpredictable across languages? If you got both right, the next sections will feel like connecting dots instead of memorizing terms. Prompt engineering is the skill of designing the text input so the model produces exactly what you need. Look at the difference. A one-line request gives you a vague, generic report. A detailed prompt that sets a persona, specifies the analysis scope, dictates length, and defines the output format turns the same model into a precise, professional analyst. This is not coding. It's communication. And it's the most immediately valuable AI skill you can learn today. No technical background required. 3 prompt styles every AI practitioner uses. Zero shot means you give the instruction with no examples. Fine for translation or summarization. Few shot adds 2 or 3 input-output pairs before the real query, which locks the model into a specific format or tone. Chain of thought tells the model to show its work before answering, which dramatically improves accuracy on math, logic, and multi-step reasoning. The rule: start with zero shot, add few shot if format drifts, and reach for chain of thought when the answer needs justification. These 4 mistakes tank AI outputs every day. The fix is simple. Place your key constraints at the very end of the prompt. Modern models pay the most attention to the last instruction. Always specify the output format you want, like JSON or a bullet list. And start your prompt with "You are a" to set the role. Think of it as briefing a highly capable but extremely literal colleague. Give them everything they need to succeed, or they'll guess. And guessing is expensive. Fine-tuning is like putting a general-purpose model through a residency. You take a foundation model that already understands language and train it further on thousands of domain-specific input-output pairs. Say, patient symptoms mapped to formal medical codes. The center of this flywheel is the fine-tuned model. The base model provides broad knowledge, the domain data teaches the specialty, and the output is a model that speaks your exact vocabulary and follows your precise formatting. Use fine-tuning when you need consistent tone or structure. Use RAG when you need live facts. Think of a foundation model as a medical student who just graduated med school. Broad general knowledge, but no specialization. Fine-tuning is like their cardiology residency. They don't relearn basic anatomy. They just specialize their existing knowledge for a specific field like reading EKGs. In practice, that means taking an open-source model and further training it on, say, thousands of historical customer support chat logs so the AI responds in the exact tone and style of your company's best human agents without needing massive prompts every time. So how do you decide? Simple rule of thumb. If the knowledge changes weekly, say, a product catalog or internal HR policy, use RAG. If you need the model to consistently output a very specific JSON schema and speak in the company's exact brand voice, fine-tune. Fine-tuning bakes behavior into the model weights. RAG fetches fresh facts on the fly. Most enterprise systems actually use both. A fine-tuned model for personality, then RAG to keep answers factually grounded. Training is where the model learns. For example, training a very large language model can run into millions of dollars and requires weeks of compute time. Inference is when you type a prompt and get an answer in seconds. The model's weights are frozen, it's not learning from your chat. A good analogy. Training is a 4-year degree. Expensive and slow. Inference is a 10-minute quiz based on what you already know. So when you're budgeting, a training run can cost millions, while serving the model costs fractions of a cent per 1,000 tokens. That's why RAG makes sense for freshness. You don't retrain the whole brain every time a policy changes. Models don't age. They just stop at their training cutoff. If a model was trained in June 2023, it has no concept of anything after that. Users often assume the chatbot is connected to the internet, but without a plugin or RAG, you're talking to a frozen snapshot. Before you trust an answer about current events, a new product, or a recent regulation, go look up the model's knowledge cutoff date in its docs. This one habit will save you from embarrassing hallucinations. These three often get lumped together, but they solve different problems. Safety is making sure the system doesn't crash or cause harm. That's red teaming and guardrails. Governance is the rules your company and regulators impose, like the EU AI Act, requiring human oversight for high-risk systems. Ethics is about values. Is that loan denial AI systematically biased against certain names? Does your facial recognition work equally well across skin tones? Concrete example. Any loan denial AI should have a human reviewer before the final decision lands. Pause the video and write down your answers. You're deploying an AI to automatically screen resumes. What's one ethical, one safety, and one governance concern? Ready? Here are sample answers. Ethical. The model could learn bias from historical hiring data, systematically rejecting candidates with names associated with a particular gender or ethnicity. Safety. An adversarial candidate might craft a resume designed to fool the AI into overscoring them. Governance. Without an audit trail, you can't prove to regulators why a candidate was rejected, and you've lost the chance for a human to catch the error. The biggest mistake teams make is treating AI ethics like a final PR checkbox. The EU AI Act categorizes AI systems by risk. High-risk systems, and hiring tools will likely fall into that category, will be subject to strict transparency and oversight requirements. So get ahead of it. Integrate bias testing into your CI pipeline. Run fairness audits before you ever demo to stakeholders, and make sure a human can override the AI's decision. And a second question. What's one key difference between AI safety and AI ethics? Safety often focuses on preventing harm, using techniques like red teaming and guardrails to ensure the system doesn't cause unintended damage. Ethics concentrates on fairness and values, ensuring the system treats everyone equitably. If that distinction is clear, you're ready to move from theory to application. Here's your starter kit to turn this knowledge into a credential and practical skill. The ISACA AI Fundamental Study Guide is around $40 for members. The exam fee is separate. Microsoft's AI 900 exam page on Microsoft Learn provides free self-paced learning content. Spend 20 minutes playing with OpenAI's tokenizer page to see how text becomes tokens, which makes API pricing crystal clear. And download Llama to run models like Llama 3 privately on your own laptop. Zero API costs, total privacy. We've covered the foundational concepts: AI, machine learning, deep learning, neural nets, LLMs, generative AI, reinforcement learning, computer vision, NLP, agents, RAG, embeddings, tokens, prompt engineering, fine-tuning, training versus inference, and responsible AI. In Part 2, we'll zoom out to the full AI ecosystem. Cloud platforms like AWS Bedrock and Azure AI, the open versus closed model debate, local AI tools you can run right now, and how to choose the right model for your specific job. If you want to level up from IT beginner to AI-capable professional, subscribe and hit the bell so you don't miss it.